the silver ion concentration squared times the oxalate ion concentration to the first. So we just plug those numbers in. Did you square that one?
First.
Okay. 2.2 times 10 to the negative fourth squared times 1.1 times 10 to the negative fourth. And we get our answer. This is going to be like, what? 5 times 10 to the negative 12th? For all these k values, just do 2 sig figs. You don't have to worry too much about sig figs. Just all the k's have 2. Any questions about this one? Okay, good. So now we're kind of rolling with these, and I'm going to ask you to try one more. So all the problems are just a little bit different from each other. You have to make sense of what it's asking for, and then do the mechanics on it. Mechanics, a physics term. By the way, you're going to take physics next year, and you'll be miserable. No, I'm pretty sure you won't. Okay, you got some direction on this one? We want the solubility, which once again is this thing right there. That's what we're trying to find. However much that dissolves, which we don't know, that's our answer. So initially those are zeros. And if this goes down by x, that's going to go up by 2x. And that goes up by x, yes? Okay, so at equilibrium, the solid has no defined concentration. This is 2x, and this one is x. So our KSP, which we know we're given in the problem, KSP is 1.2 times 10 to the negative fifth, equals this term squared, 2x quantity squared, and then times an x. So that right side of the equation is 4x cubed. Yeah? And you can solve for x if you have something equal to 4x cubed. Divide by 4 and take the cube root. I think this is our first cube root. Yes? Yeah, this is like 0.0, I can't remember now. 1,4? And remember, solubility is measured in molarity. So just watch out. We're used to, we did an entire chapter. I don't think there was a single coefficient in the buffer chapter. So that 2 up there, we're not used to it anymore. But just watch out for it now. It's not uncommon to have coefficients because you don't always have a 1-to-1 charge balancing kind of ratio. So you'll have coefficients in this chapter. Just one other thing that I want to show you, and then we're going to be done for the day. Sometimes you're going to be asked to compare the solubilities of 2 compounds. Most carbonates are not very soluble. Most chromates are not very soluble. So you're given the 2 KSP values of these 2. Which is more soluble? Between the 2 that aren't very soluble, which one is more soluble? So if you're given the KSPs, does that make it obvious which one is the more soluble one? Seems like the one with the higher KSP is going to be the more soluble. I'd like to answer that question definitively. I'm going to ask you not to write down. I've got something that is covered up right now. I'm going to uncover it and show you something. Don't try to copy everything down. I think we can summarize without having every little detail, and you'll be fine with it. So given the KSPs, again, not writing any of this down, let's just take a look at the ice table for each dissolving solid. That means this. This compound, again, you're not writing any of this down, are you? No, just watch. We don't know what the solubility is. In fact, that's what the question is. What is the solubility? So we'll just call the solubility X for this one. And if that goes down by X, that's going to go up by X, and so is that. 1-to-1 ratio. So that's nothing, and that's an X, and that's an X. So that means this. The KSP for the nickel carbonate, which is given to us, 1.4 times 10 to the negative 7, equals X squared. So X, the solubility, is going to be the square root of that number. Yeah? Over here, the same kind of thing. Instead of using X, I'll use Z. So initially, those are zeros. This is going to go down by Z. Those go up by Z. And therefore, at equilibrium, you got Z and Z. It's all 1-to-1. KSP for this one is 8.5 times 10 to the negative 11. And that's equal to Z squared. So the solubility can be compared. This one is the square root of that number. This one is the square root of that number. So would you agree, and so Hill was saying at the very beginning, if you just know the KSP values, the one with the higher KSP is going to be the more soluble one. Would you agree that this square root is bigger than that square root? So yeah, this one is the more soluble. It's a bigger K value. If it were always that easy, though. You know that we've been together long enough. We know what's coming, right?
I hope you just stop here.
Oh no, I got time, don't worry. Same question. 2 different compounds. This time, we're going to compare MnS, manganese sulfide, to iron 2 hydroxide. And the KSPs are given to you. You know I'm up to something. Which one is more soluble? The one with the higher K value? Well, let me just ask you, before we do anything else, I want you to compare this pair of ions, or ionic compounds. What do these 2 have in common, where we could just look at this and say, oh yeah, that one's got the higher K value, so that's the more soluble, and that was right. Over here, yeah, this one is the higher K value, but it's going to turn out to not be the more soluble. Why? You said something about coefficients. What about coefficients?
The other one, there's a 2. There's going to be a 2.
Yeah, yeah. This one, when it dissolves, gives off 2 ions. See that? You're going to get a manganese and a sulfide ion. This one gives off 3. Does that make a difference? Yes, it makes a difference. So again, don't write this down. I'll show you that it's not going to benefit you to go back and look at what we wrote here. Manganese sulfide, when it dissolves, it's going to go down by X. These are going to go up by X. And therefore, the KSP, which is 2.3 times 10 to the negative 13th, equals X squared. So the square root of that would be the solubility. Yes? Over here, this is going to go down and dissolve by some amount Z. This is going to go up by Z. This is going to go up by 2Z. Does it matter? Oh yeah, it matters. Because when we do the K expression on this one, KSP equals Z times 2Z squared, which is 4Z cubed. So the X term over here, the solubility, is the square root of 2.3 times 10 to the negative 13. Over here, the Z value is going to be the square root of, not the square root, sorry, what root? The cube root. The cube root of, well, you got to take that 4 out of there too. So it's 1.8 times 10 to the negative 15th over 4, and then take a cube root of that. What just happened? Can you just estimate the square root of the 10 to the negative 13th versus the cube root of the 10 to the negative 15th? Which one is a bigger answer? That one, isn't it? Just looking at the powers on the 10, square root of that is going to be 10 to the negative 6.5. This cube root is going to be 10 to the negative 5th. Yeah? So this one is a higher solubility. So how could we summarize this? When you're comparing the solubility of two things, if they give off the same number of ions like these did, the one with the higher K immediately is going to be the more soluble one. If they don't give off the same number of ions like these did, you have to compare. You could do all the work, that would be fine, or just compare. Figure out how many ions they give off and take that root of their K. Like that gave off 2, take the square root. This gave off 3 ions, take the cube root. And then whichever root is going to give you a higher answer, that's the more soluble. So just watch out for that kind of thing. I leave you with that. You have the rest of the hour now. Well, more than 20 minutes. You can finish or work on at least the lab. Does anybody need their lab printed still, their graph printed? Okay, I'll leave you alone.